It's time for us to start. Okay. So, charging on, take care. Recording started. Well, quickly, I'll come back to the topic. Okay. So, what we have covered in the last session was regarding, I think I have explained it clearly about the eccentricity and all. I think I have devoted sufficient time on the this part. Okay, along with this one example, one solved example for you. Okay, so that it can be done. But the thing is, I have done it. I have mentioned it in the form of the rows, which it should not be. It should be in the form of columns. Okay. So, and that also I have explained what is the interpretation when I write it in the column means when I take the average or min of all those columns, and what is the interpretation when I take it for the row. Okay, ideally it should be row because these are the main node and these are the neighbors. So A and all those who are non-zeros are the neighbors of A. We can say nodes with the path from A. So this is A from A to all other nodes, and this column will be from all other nodes to A. Simple. So before moving ahead, any explanation to be given regarding any of those values? I hope that's clear. I need a small confirmation. Was that clear to you all? Was that clear? Am I audible?
Yes, sir.
Okay, okay. So that means no reply means. So, okay, chalo. So let's quickly move ahead towards some more topics. Okay. Those random graphs we will discuss again in full depth. I think we will denote around half an hour for those random graph when we will be talking about the generative models. Okay, so as of now, I've just included it. We will have a full description about those random graph later on. Okay, then this degree, diameter and all is being covered. And this is the examples where which gives, this is the data given by in some research paper about the diameter of various kinds of a graph. Okay, so let's move ahead in the direction in which we were working. So we have covered, we have talked about those distance, degree, distribution, radius and diameters. Now we'll quickly for around 15 minutes, 15 to 20 minutes, we will be talking about patterns in the static graph, in the dynamic graph as well. So the case to handle the dynamic graph is solve it on a static graph, but iterate it again, repeat it again after some interval of time. So in this way, you can handle the dynamic graph. So this pattern we have discussed. Okay, so just by looking at the diameter, just by extracting out those numbers and all, we can have some intuition about the structural properties, or we can say structural information. We can have the structural information of the graph. Now we'll discuss a bit about power law. So power law in mathematics, what is it? Anything which is two scalar values or two values which are proportional to each other. Okay, so that we call it as a power law. For example, area of a square. So the formula for the area of the square is of square of any side is the side of their square. Okay. So what is the law in it? So if you change, so suppose for example, if the side of the square is 2, okay, side is 2, then area will be 4. If side is 3, area will be 9. So that means with some change in one variable, there is some appropriate or proportional change in the final value. So power law is known as a scaling law. A relative change in one quantity result in proportional relative change in the another. So if this relation holds, then that type of law will be called as a scaling law. Okay, not necessary it should be always a positive one. It can also be a negative relation as well. For example, the force of attraction or magnetic force or electromagnetic force. Okay, so in that case, the force of attraction between two heavenly bodies is inversely proportional to the square of their distance between them. Or force of attraction, electromagnetic force between them is inversely. So some in that case, either in that way or in this way. Okay, so y equals to x to the power a or y equals to 1 upon x to the power a. So x to the power a will be directly proportional. 1 by x to the power a will be inversely proportional. So either in a positive direction or in a negative direction. If this relation hold, we call it as a power law. Okay. General term, whenever the proportional term, so suppose for example, if I say okay, y is proportional to x to the power 1.44 something, so usually y equals to k x to the power 1.44, usually what we used to do earlier. Okay, so that means whenever I want to remove the proportional sign and equate it to and replace it with some equal sign, I multiply the whole factor by some constant factor a. Okay, so the general power law is y equals to kx to the power alpha. So where x and y are the variable of interest and alpha is the exponent, it can be positive, it can be negative, and k is the constant. Okay, so this is a power law. But what is the interpretation or what is the application of a power law in our day-to-day life? Because power law holds in every phase of our life and most probably in every activity throughout the world. Okay, so it is a phenomena. So power law can be described as a phenomena where a small item of a small number of items is clustered at the top of the distribution or at the bottom of the distribution, taking up 95% of all the resources. Okay, which means the simple sentence is a small amount of occurrence is common while large occurrence are rare. Okay, so what does this mean? That most of the time what we do has no impact. Okay, there are only small things which have a higher impact on the life. So that's also a power law, which means suppose for example the incidents, your decisions in your life, at every second my brain is processing something and deciding something and taking a decision. Okay, even if I'm speaking, then also my brain is taking a decision, sending signals to my uh, vocal cord, and then based on those decisions I am able to pronounce the word. Even for the movement of hand or whatever it be, some decision activities are being performed and decisions are being taken. to take the class, sit on the desk, start the class on time, starting the recording, whatever it be. So I am taking hundreds and thousands and millions of decisions every day. Okay, usually some important also, whether to buy something or not or something. Many decisions we used to take, smaller or bigger, very big or something. But there are very few decisions throughout your life that may have consequences of or we can say a bigger impact. Okay, so that's also a power law. So whatever you do most of the time may doesn't have any impact on your life, but something or a small number of decisions has a huge impact on the disease, impact on your life. Okay. Second thing, that was a weird example, but let me go through the technique, places where the power law phenomena has been observed. For example, magnitude of earthquakes. As you know, hundreds and thousands of earthquake occurs on Earth on a whole day, daily. Okay, in some part or the other, even with the minor uh, 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 zero point 0.5 or zero point 0.2 reactor scale, but the number of earthquake that occurs daily on the Earth or that occurs on the Earth are very huge. But there are only few earthquake beyond the Richter scale of 7, which has a high impact on mankind. Okay, so that's also power law. So most of the earthquake have no impact, but there are only few who have a very high impact. Size of the craters on the moon. So there are millions of craters on the moon, but there are few very large, which are visible, which are because of some bigger impact. Solar flares. Solar flares comes out of the sun in every second, in every milliseconds. But there are very few solar flares that have an impact on the environment of particular planet. Okay, there are very few. Once in a year, twice in a year, once in a month, whatever it be. But that activity happens at every second, at every microsecond. But impactful entry is very rare. Size of the cities according to the populations. So there are millions of cities throughout the world, but there are few which have a very high population, which have a very dense population. So they are countable. Number of persons living into that city. So even in Delhi, around suppose 2 crore or 4 crores persons are staying, are living. Okay. But there are very few cities. There are many cities having the, or many places having the total population count of 2 lakh, 3 lakh, or 4,000 something. Some villages have a population of 200, even 400 or something. Okay, so there are many residential areas, but there are very few who are occupying, who are holding large number of individuals. Size of the corporations. There are many corporations with a smaller size, but there are very few which controls the market. Trading volumes on a stock market. At every second, some trades happen. But there are few ups and downs. There are few trades which affect the stock market. Same word frequencies. There are many, but you yourself, if you keep a count of words to be used, the number of words that you frequently used will be not more than 100 or 1,000. Okay, so because that is your vocabulary. So in that case, all those phenomena are power law. But why I'm talking about all those things, all those real life problem or real life scenarios, because in here in this case, we will be converting the real life problems, all the real life problems into a mathematical problems. And if we have converted into a mathematics, then definitely we can convert it. We can try to solve it in the form of a graph. And if graph, then we can apply graph neural network. So somehow on whatever problem we are working will be a real-time problem. And all the real-time scenarios have a power law in it. they exhibits power law. So definitely the graph on which you will be working, which have been constructed out of certain real life scenarios. So definitely this graph will also have a power law. Okay. So it's like necessary evil, like a fraction. It is a part of your day-to-day life. We know that fraction is bad. It is it because of it. There's lot of fuel consumption and many more things, but it is a part of your life. Same is the case power law. Okay, so every real-time scenarios, every activity exhibit that law. So if you are converting that into a graph, then graph should also have the power law in it. If not, if somehow you can identify, okay, the power law is not being is not exhibited in your graph, so that means there's something wrong. You are not able to convert your real-time problem into a graph problem, because if there is no power law, that means your creation of a problem, or we can say conversion of a problem, is not correct. You have missed something. You're doing something wrong. But how to plot it? So basically, as this, I'll be dealing with a very high values of the of exponential powers. So definitely, to make them visible in a graph, we will be doing it on the logarithmic scale. Okay, because log scale um make we can say makes the problem linear, visible in your range. So this is the graph whenever you type the power law in on a Google. So this is the graph taken from the Wikipedia that exhibits toward the power law. So what does it mean? It has a few observations. Something is painted in green, something is painted in yellow. There are very extreme values. So that means, suppose if this is a scale, so 0, 1, 2, 3, something. Okay. So that means there are very few values, very few count number of values having very high magnitude. Okay. And later towards the end, towards this, so there'll be a large number of values. So if this is my count, okay, so and this is something, some magnitude. Okay, so that means there are very few values having a highest magnitude, and there are large number of values having lower magnitude, lower value. So that is a power law. So an example of a power law graph being used to demonstrate the ranking of a popularity: to the right is a long tail, and to the left there are few that dominates. So if this value is very high, so if I take an average, if I find out the mean of this distribution, the mean of the distribution will be towards the extreme values. So it is also sometime it is also mentioned as 80-20 rule. 80-20 rules means 80% of population. For example, the general statement is 80% of the population is controlled by 20% of individuals. 80% of wealth is acquired by 20% of industrialists, or 20% of humans throughout the world, something like this. Okay, so that is the power law. There are a few similar distributions and law. Pareto effect, which states that 80% of effect come from 20% of causes. Almost the same thing what power law is talking about. Most of what we do has a little impact on your life. There are very few decisions which have a higher impact. The another distribution, we call it as Zipf's law. So Zipf's law usually refers to the frequency of the event related to its rank. Okay, so that means Zipf's law states that given a list of most frequent word in an arbitrary book, so you take any book and you perform a word count. Okay, word count and their frequency count. So given a list of most frequent word in an arbitrary book, what the observation was, the observation is the most frequent word will appear twice as often as the second most frequent word. So for example, if your most frequent word appears 10,000 times, then the second frequent word will be half of it, 5,000 only. The third most frequent word will be 2,500, and so on. So which will appear twice as often as the third most frequent word, and so on. So that means the frequency of the word that you usually use are related to double of it. So the most frequent word is twice as large as the second most frequent word, and so on. So the simplest form of all the Zipf's laws and Pareto law and all are called as power law. So they all belongs to the superset usually called power law. So there are few properties of a power law. It is scale invariant. Suppose for example, if the power law states that f is a x to the power minus k. Now if you replace x by cx, okay, you just scale it up. Okay, now scaling can be in two ways: scale up or scale down also. How you perform a scale up? So suppose for example you are working on a variable x. Now if you replace the variable by 2x or 3x or 4x in some way, now you have replaced x by 4x. So that means now this value y, 4x y, will be 4 times larger than my original value. So I've made the thing bigger. Okay. Alternatively, it's not the case that always I am scaling up. I can also scale it down. X by 4. Divide the number by 4. Okay. Or reduce it to half. X by 2. I'm reducing the value by 2. Ultimately, what does it mean? It means that if you open it up, it will be something like this: 4 to the power k into xk. This k will be a constant. Or if it is scaled down, x to the power k upon 4 to the power k. Or if it is half, then x to the power k by 2 to the power k. As this was a constant, this is a constant. So suppose for example, a is already there. Okay. Now, so that means a into 4k, I can put them together. A is again a constant, and 4 to the power k is also a constant. So I can multiply two constant and I can replace it by a second one, capital A into x to the power k. What then? I've just changed the constant, but the relation remains the same. Fx equals to a. Now a may have a different value, but fx, the ultimate relation is fx equals to a into x to the power k. Or if it is scaled down, then a 4 to the power k xk, this can also be replaced by capital A x to the power k. So either a scale up or a scale down, it doesn't have any impact. The value of the constant may differ, but ultimately rule or the law will have a same proportion. Same law will remain the same. So this power law is scale invariant. If you increase the size or decrease the size, it doesn't have any impact on the law. The law will still be there. So that is a scaling by a constant simply multiplies the original power law relation by some constant. But still that relation remains the same. So which means that all power law with a particular scaling exponent are equivalent up to the constant factor. Since every simple scaled version, if every since each is a scaled version of the another. So that means all power laws are same. They have a different A and a different K. And A and K may have a different type of relation, but they all can be represented in the form of xa to the power x a x to the power minus k. A and k may differ, but all the power law, all the laws are same. They all are equivalent. Okay, with different values of constant factors. Second property is the well-defined average value is lacking. So lack of well-defined average value. So power law x to the power minus k has a well-defined mean over a range from closed interval 1 to infinity. So that means x can have the value from 1 to infinity. Okay, less than 1 not. So x can have the value, any value from 1 till infinity, but only if k is greater than 2. So if this is the condition, if this condition holds for the range of variables, then my power law will have a definite mean. Okay, mean means the balancing point. But if the value is greater than 3 and x is from 1 to infinity, then that power law will also have a finite variance. If it is between if the value of k is between 2 and 3, then it will have only mean but no variance. But if k is greater than 3, suppose k equals to 4, then the power law will have a mean as well as have the variance. So most identified power laws in nature exponents such as the mean is well defined, but the variance is not, implies that a black swan wave. So in most of those activity, what does this mean? This says that for all real-time scenarios, most of those real-time scenario, the value is less than 3. The value of k is less than 3 for most of the scenarios. So mean is well defined, but variance is not. Most identified power law in nature have the exponent such that this is the case, means all the means whatever the power law that you exhibits in the nature has a value of k less than 3. That is the interpretation. Okay. And the second is universality, means you will find this law everywhere. In terms of distribution, a random variable is distributed according to the power law when the probability density function is given in the form of ax to the power minus gamma, where gamma is greater than 1 and x is greater than some threshold, which is x min. The extra gamma greater than 1 requirement ensures that px, the probability distribution, can be normalized. The power law with gamma value less than 1 rarely occurs in nature. That means for most of the scenarios, the gamma is greater than 1. And the significance of law distribution is that it decays much slower. Okay, it decays much slower as x tends to infinity. So that means the tail is heavy. The decay method is very slower. Okay, towards the initially it will be very fast, but then it will be very slow. A power law distribution would be much more likely to have a nodes with a very high degree than in Gaussian distribution. Okay, so this is just a law that we will observe, and I think now everything I have explained, because this slides I'm going to skip Hop, I have already talked about. I have already talked about the neighborhood NHU. Okay. NH is summation of all those U's where NH belongs to U means I'm talking about the neighborhood search. All the neighborhood of the node U. Okay. So what is the impact and how these hops have been calculated? So one hop means A, two hop adjacency matrix A square, three hop A cube, and so on. I think I have already explained you in my last session okay, how to calculate the hop matrix. Okay, it's nothing, it's just a square of the matrix of the adjacency matrix. Okay, effective diameter and eccentricity, why 90% only? Because I'm allowed to skip 10% which are degrading my result. Characteristics, path length, average diameter and eccentricity. Okay. Okay. So any doubt so far? Just a theory part. You'll have to just understand and nothing else.
So just
That
one question here actually. Here in the power law, can you go, yeah, few more slides back? Yeah.
stop me where you want.
Yeah, yeah. No, go further back. Yeah, this one. Yeah. So why we say this? Next slide, sir. Maybe I missed it. It must be trivial, but I just wanted to understand further. This
This
f of x is equal to no. The next slide. The-
this
Where
one.
we yeah,
Hmm.
this one. F of x is equal to a into x raised to minus a minus k. Why we say minus k out there? Like why not just k?
हाँ ठीक है मतलब because minus k means I'm taking care of positives and negative because this k
Okay,
this law can be positive or negative. So
right.
they can be proportional means directly proportional and inversely proportional as well.
Oh, okay, okay,
ठीक है? So
okay.
in that case, if I want to make it directly proportional, then alpha, then I can choose some alpha as my from the range of negative values. So negative will make a positive, and
Okay, got
and
it, sir.
and okay. So ideally, हाँ ठीक है. Your doubt is clear. The power law should be in this way. It should be written in this way. But
Right.
just to take care, मतलब just to take care of the proportional, positive proportional and negative proportional,
So
in this
we can
case,
say this is like generalized form of the
generalized.
yeah, okay.
Okay. And the second thing is the normally, or we can say most of the time, in whatever phenomena that we have observed on all the phenomena, okay, in all those, most of those phenomena, the relation is inversely proportional. Size of the
Okay.
earthquake. So there are huge number of earthquake that occurs on Earth on a year, but there are very few who have a large impact. Something.
Hmm. Oh,
Most,
okay.
so by default relation, most of them are inversely relation, so they have kept it minus. But your point is good, it can be positive also, but it's just a notation given by them,
Okay. Thanks, sir.
by emphasizing more it is more towards the
Inversibility. Yeah.
in inversely proportional relation.
Okay.
Huh. Any more
Thank you.
queries? Thank
Thank you.
you. Any more? No more queries? Result?
Just one question here. I mean, this power law is okay, actually, I got it. But how will we going to use in GNN, right? I mean, this is a mathematical concept, and
Hmm.
either it will be used in the data side or in the model side.
Okay, fine.
Training, I mean to say
So
training side.
fine.
Mhm.
The answer will be a bit weird. This is the power law. You won't be able to implement it. You can only observe the power law into your given graph just to check whether if the power law is there, that means your graph is, well, you have realistically converted your problem into a graph problem. So suppose, for example, if power law is not there, then definitely you have made something wrong while converting that problem into a graphical problems. So power law will be something that you observe in a graph to ensure that if it is there, then that means my conversion, my conversion of a problem into a graphical problem is correct. The absence of power law can can give you an alarm. Okay, if this is not there, so that means either I have not converted it correctly or I have done something wrong. So power law will be something that you observed, that you visualize in order to ensure that, okay, so that means if power law is there, that means my interpretation is correct. So you won't be able to use it. We won't be using this power law anywhere throughout the GNN, throughout the course. But we'll observe, okay, if power law is there, that whatever the result will be. So if those results are in accordance with the power law, so that means the result may be correct. Absence can raise an alarm.
Okay. So, and how will we going to observe in the graph whether it is available or not?
Fine.
Because
This screen will give you one example. This graph will give you one example of observing the existence of power law. Okay, any more queries? I'll explain it. No, not to worry. I'll explain this graph. Any more queries? There's no stupid question. Whatever comes in your mind, you can raise it, because I'm explaining you those topic in a stupid way. So that means nothing is stupid. If I can explain you in this way, you can also ask me some questions in that way also. No queries? Okay, fine. So there was a mathematician, there was a researcher with the name Border. In the year 2000, what he did, he just performed a web scraping on a graph and count the, on a directed graph, and just count the in degrees and out degrees of a node. Okay. So he, suppose for example, he performed a just for example, suppose I performed a web scraping on Google. Okay, with some seed, some initial text, I fired a query on Google, and then based on that, I perform a web scraping. Web scraping means exhaustive web scraping. I take care of all the web pages that exist on the internet. Okay, and that is a directed graph. Based on that, I count, I convert this that web scraping into a graph based on their degree. And as this is a directed graph, I count the in degree and out degree of each node of a graph. Okay. Now, so suppose he also did the same. He performed a web scraping, convert that web scraping in the form of a graph, in the form of a directed graph, and then count the in degree and out degree of a graph. And he performed it 2 times, one in May 99, and on the same graph, he performed that web scraping again on October 99. Okay, so he have data of in degrees of 2 different times, May 99 and October 99, and out degree of May 99 and October 99. Okay, now what he have is, he have the graph with, so means number, those nodes will be the number of web pages. So the size of the graph will be equivalent to the number of nodes. And that will be equivalent to the number of web pages. Clear? And each node will have some in degree and will have some out degree. Easy. Now he just plot the in an ascending order of their in degree. So number of web pages in the ascending order of their in degree and out degree. So what he observed was, he observed that there were very few, less than 10, in both the years, light green and we can say red and red and blue. Okay, both the time. He found that there are very few nodes. Sorry, there are large number of nodes from the range of e to the power 6 to e to the power 8. So e to the power 6 to e to the power 8 number of web pages, okay, was having lower in degree. So e to the power 6 to 8 to the power 8 number of web pages were having low in degree, less than 10, with in degree less than 10. So if I do have a graph of a very huge graph, okay, number of web pages e to the power 10, with in degree raised to e to the power 10, 10 to the power 5, suppose. Okay, so 10 to the power 5 means you need tens, 100,000, 10,000 lakh, 1 lakh of nodes. But there were large number of nodes having smaller in degree and smaller out degree. Okay, suppose it was 10 and it comes to be 7 or 8 or 9. So that means there were large number of web pages having degree less than 10. The other observation was there were very small number of nodes or web pages in the range of 100 having very high in degree. So this is the second observation. So the first observation was key large number of web pages were having lower in degree. Okay, either in degree or out degree. And the second observation was around 100 web pages. These are the web pages now. There were 100 web pages. Means there were few web pages with, so 100 means few. There were few web pages with degree either in the form of in degree or out degree of the range. Suppose, for example, 10, 100, suppose 1,000, then 10,000. So around 80,000 or 1 lakh. Okay, so in other sense, in general, I can say there were very few web pages with a very high degree, either in degree or out degree. Okay, so that means if that phenomena exhibits with the alpha values ranges from 2 to 3, so that means he says that, what does he try to infer? He tries to infer that even the degree distribution in a real graph exhibits the power law. He didn't do anything. He just observed the degree with respect to number of web pages, in degree and out degree. Okay, he performed it at a 2 different times so that he can ensure that it is not just by somehow at that time it may happen. No, you can do it now also, 2025 also. So degree distribution 2020, or someone might have published that graph again. There also the values may have changed, but the relation would have remained. The relation will remain the same. There'll be a large number of web pages having smaller in degree, and there'll be very there will be a large number of web pages having smaller in degree, and there will be smaller number of web pages having high degree. So that is a power law. And that power law also, I'll explain this clustering coefficient later on. That's not the case that it exhibits in the form of connectivity only. If I'm trying to find out the triangles in a graph, okay? Now, why triangles are important for me in terms of connectivity? Because first of all, triangle gives me a way to connect to as a recommendation system. So A is related to B, B is related to C. So in that sense, A can also be related to C. Okay, so that is the easiest, or we can say easiest way to represent or to use the recommendation system. But where else the triangles are important for me in terms of connectivity? Why? What is a triangle basically? It is the simplest triangle is the basic building block of complete graph of higher order. Now, why I'm bothered about complete graph? Because complete graphs are responsible for their connectivity. If graph is almost complete, means the density, the connectivity is at the peak. The total distance between every two pair of node will be a direct edge if my graph is complete. So a graph is said to be complete if one node of a graph is connected to every other node of a graph by a direct edge. So what should be the path length of all the nodes? Path length will be 1. So that means every individual is connected to every other individual of a world by a direct edge. Means everyone knows everybody in terms of relation. Okay. Now, relaxed version, there can be some intermediate friend, 6 degrees of separations. So that means in terms of connectivity, in terms of density, triangles plays an important role. So it means if there are more number of triangles, that means the bonding or the connectivity may be more dense. So that's why triangle are important to the graph. Okay. The second reason is if so, the triangle is the smallest complete graph in a loop. If there is a loop, if loops are okay, even the smallest complete graph, even in that case, general, a single node by itself is a complete graph of one node. A edge is a complete graph of two nodes, but there's no cycle in it. With minimum with the cycle in it, triangle is the first complete graph. That's why triangle is important. Now, why I called it as a basic building block? Suppose what is the complete graph of 4 nodes? This is a complete graph of 4 nodes. Can I construct this by using a number of triangles? Yes, I can. One triangle. Okay. The other triangle. And one is this, and one is this. Suppose, for example, I can create, although I may require more triangles, but can I create a complete graph of 4 nodes by 3 triangles? By merging 3 triangles? Yes, I can. Or in other way, if I merge 3 triangles, one triangle, two triangle, and then three triangle. I will get a triangle. I will get a complete graph of 4 nodes. Can I construct a complete graph of 5 nodes? I can by a number of triangles. I'll be doing it by using the triangles only. Okay. One triangle, two triangle, three triangles. Okay. So 1, 2, 3, 4. 1, 2, 3, 4. Fine. 1, 2. Okay. And then this again will be a triangle. Okay. Somehow, let me draw it clearly. Now I will avoid overlapping of edges. Okay. So 1, 2, 3. One triangle. 1, 2, 3. 1. That's again a triangle. So 1, 2, 3. Okay. So that means this is connected. This is connected. 1, 2. So this is connected to this. This node is connected to this. Let me connect with this node. Okay. So that means 1, 2, 3. 1, 2, 3. 1, 2, 3. This is connected. This is connected. Let me connect. So 1, 2, and 3. So I can create a complete graph of 5 node by a slightly more, but some number of triangles. And so on. Can I do it for 6, 7, 8, or 9, 10? Yes, I can. So that's why triangles are important for me. And the two counting of triangles are important for me. Okay. So that's why triangles are important in terms of connectivity for a graph. And based on it, I can sense about the connectivity. If there are more number of triangles, then graph will be almost complete or the connectivity will be very dense. And they can also be used as a part of recommendation, because friends of a friends often become friends by themselves. So that's why, or increasing the neighborhood search, by increasing the neighborhood connectivity. For them, triangles are important. So what the other researcher had done, what he did nothing. He just plot. So he just count the triangles in a graph and plot in a different way. So let del be the number of triangles in a graph. So he counted the triangles on a triangles in a graph. How many triangles in a graph? Means cycle of part 3. You have this library function. I think in the webinar itself, Professor Vipin has explained you this. Okay, so this is one. He count the number of triangles, and the second factor was del I means the number of triangles in which each node participate. So the total number of triangles in a graph, as well as this value is associated with each edge or node. Initially, node also. Okay, so a value was calculated for each node in which in how many times in how many triangles this particular node is participating. So that means this node it's participating in one triangle, the other triangle, okay, and this triangle 3, and any more triangle? No. So this node is participating in three triangles. One is this. If I 3, 4, 5. So how many triangles in which this node 3 is participating? 3, 4, 5. Then 1, 2, 3. Then 2, 3, 4. Is there any more triangle? Yes. 2, 3, 5. Okay. So 1, 2, 3. So overall, this node is participating in 3 triangles. So this del I was the value associated with each node of a graph, as well as this del was the overall count of number of triangles in a graph. So he plot. So the first triangle participation law, TPL, says that the distribution of delta I follows a power law with an exponent of 6 sigma. So this, what does this convey? The triangle power law intuitively state that while many nodes have only few triangles in their neighborhood, a few nodes participate in a huge number of triangles. There are only few nodes who are participating in a huge number of triangles. So suppose there are 100 nodes which are participating in 10 to the power 5 or 10 to the power 6 number of triangles. And there are large number of nodes who participate in a fewer triangles. Similar like in degree and out degree, the degree and number of web pages. So the number of triangles delta I for a node I is related to the cluster. Okay, fine. This I'll explain later on.
Sir, one doubt.
Ji.
Consider, let's say, like I have four vertices, and this is a directed graph. So one vertices is connected with another vertex with a single direction. So let's say I have four edges. Now with these four edges, it, let's say, it forms a rectangle with four vertices. Now, do you have to consider here the triangle because the diagonal one
There's
is
no triangle.
missing?
So
No
there is no
triangle.
triangle in this graph.
Mhm. Okay, and if it is diagonally also connected, then there are two, let's say, two triangles are there. Then what does this triangle convey? Like each edge is associated with a two triangle. Let's say two diagonals are associated with two triangles. Then what does it convey? The what should we infer from this?
Acha, in that case, suppose for example, by default, I was talking about the underlying undirected graph because computation of triangle is easy in an undirected graph. For a directed graph, if this is my scenario, so that means number of triangles will be, this is one, ABC is one, okay. Then BCD, if the direction is in this way, then it can have one triangle. But if the direction is in this way, suppose for example, if the direction of this edge is this, then I don't think this will be a triangle because B and C, B to D, then B to C, then C to D. So there is no, there will be only one triangle in that case. It may be possible that even it doesn't have any triangle, even though it is an underlying graph can be complete. Okay. Now, so suppose if there can be one triangle. In that case, B, if this is the direction, then A to B, B to D, and D to A will be one triangle. If I reverse the direction, then will there be still a triangle? There can be
No.
C, B to C, D, C to D, then D to B will be a different triangle. Okay, they can be triangle, but in that case, there will be only one triangle. Okay, so the triangles in a graph, suppose, and for example, if this may be the direction, then also there will be one triangle, A to C, C to D, and D to A. But okay, but in that case, the number of, if this is my graph, number of triangles will be 2.
So directed graph and undirected graph would have a different analogy in that case, right?
Ah,
Because
okay.
although
Most of,
all the nodes are here, we see like it's connected, but the direction matters here. So basically, and because of that, we are not counting each and every triangle which we visibly see, but because of the direction.
correct. But in that case also, but malabba, in that case, if I, so the diameter and the all the other the network measures will also have a different values.
Right.
This will have a different I mean, if you execute that, suppose for example where it is, here it is. So eccentricity for a single graph, for a simple graph will be something like this. For a directed graph, it was something else. if you do remember. So, but the underlying thing was, which I was trying to explain was, in terms of triangle, even the number of triangles in a graph, in an undirected graph, they also exhibits the power law. So that power law is called as triangle power law. So if you count the number of triangles and then if you check, okay, so if triangle power law exhibits, then you can say, okay, so that means in terms of connectivity, the power law exhibits. So this is just we observe in the graph. I hope I have resolved your query, whatever your query was.
Yes, sir.
Okay. I'll explain this clustering coefficient later on. Okay, let me focus more on power law. Even degree triangle power law. So there was a researcher with the name Kang in 2008. He studied the Twitter graph and he plotted nothing, the degree of each node as well as the number of triangles in which that node was participating. So he just plotted those two values on a Twitter graph, degree of that node, degree of a node, as well as versus the number of triangles in which that node was participating with respect to I for a Twitter account. So what he observed in that case was that also exhibits power law, and he named it as a degree triangle power law. Okay, so in the earlier year, around 10 to 15 years ago, making a publication in a graph was very easy because there was very lesser amount of work done in that area. Big graph, big data mining. Okay, so we see that in that case, what was his observations? So he observed that the celebrities with the celebrities have higher degree and reasonably connected followers, and some users having super linear relationship of degree versus triangle. So linear, sublinear, superlinear, exponential type of a thing. So those account will have a relatively smaller degree, was 10 to the power 4. So that means there were 10 to the power 4 accounts having smaller degree, but they participate in around 10 to the power 4, sorry, 10 to the power 8 triangles. Okay, so that means there were around unit tens, 100,000. So there were 10,000 users. They participate in 10 to the power 8 triangles. So on inspection shows that these are the account for the adult advertisers and possibly the same person with the multiple account following each other to artificially boost the degree and or the credibility. So when those set of nodes have exhibiting those power law were analyzed, so that can be used to identify or to extract out the outliers. Okay, this may be the spam. Okay, so users, if you can also check somehow if you have the calling data. Okay, means calling data means the telecom network. Okay, who calls to whom? Now, usually how much calls you make? 10, 15, not more than that. And it is for most of us. Usually most of us used to make around 10 calls, 10 to 15 calls. Sometime it may exceed to 20, 30, but usually around 5, 10 calls per day. Sometimes zero, nobody calls. Okay, so that means if the in degree or out, and how many calls you make, unless it is very emergency and you have some task to do, then you will make 20, 30 calls, 20, 30 hardly, but 15, 20 calls, but usually 3 or 5 calls, even the duration of the calls also. Okay, so in that case, if you plot the call graph, then there'll be very few numbers, very few phone numbers whose outgoing calls are very high. Those are the telecallers, either through human telecallers or it may be through IVR also. Okay, if it is through phone, it will have some in degree. So there may be some phones in some phone numbers. If you call back, they will connect you to the some humans. Some IVRs, if it is through some softwares, so if you call back to those numbers, the call will not connect. So in that case, in that call graph, if some users has an in degree 0 but have a high out degree, so that means they are the spam callers using IVRs. Even suppose, for example, even though if they have some in degree 2 or 3, okay, so that means they may be the insurance callers using a humans. The humans are using their own phone to make a call. So whenever they can receive it back also. So insurance guy used to receive those calls back. So that can also be used to find an outliers and all. Okay. So simply that's we can also utilize this triangle and any of those power law for our own activities also. So degree power law plots can be used to spot potentially dangerous accounts such as adult advertisers or spammers. So he did nothing. He just plot two things in a graph after performing a web scraping, and then he got the paper published. Even that minor work was published. Okay. Now there's one more word which is clustering coefficient. Okay. So apart from the small diameter, I think now you are aware about what a small diameter is. Okay. Small diameter means reachability with a hop distance of 6 or less than 6. So apart from the small diameter diameter in a small world network, the clustering coefficient is also high. Okay. Now, what is a clustering coefficient and what does it do? Clustering coefficient measures the degree to which the node in a graph tends to cluster together. So it is it gives me the tendency that the nodes in the graph tends to come together to increase the connectivity. Okay. So it has a relatively high values in many graphs. So if my graph is very dense, its clustering coefficient will be very high. How can I measure it? Again, in the form of triangles. So if the number of triangles are high, the clustering coefficient will be high. So that is an observation, that is the trend. How we can calculate a number, which I call it as clustering coefficient. So it will be a formula which will be 3 times, I'll explain you what does this 3 means. 3 times the triangles in the graph divided by, that is a normalizing factor. The denominator is a normalizing factor. So divided by the connected triples in a graph. Now, why I'm focusing on triangle, I have already explained. It is the smallest complete graph. Okay. So number of triangles, how many number of triangles in it, divided by how many number of triples in it. So triples means path length of 2. Okay, connected triples, 3 nodes connected together. So 3 nodes can be connected together in this way, and 3 nodes can be connected together in this way also. So this contains triangles plus triples. This is the denominator, so that's why this will be the normalizing factor. And numerator will be number of triangles. So total number of triangles upon total number of connected triples in a graph, which include the triangles and the open path of length 2. Summation of sum of both. Okay, so number of triangles divided by number of connected triples in a graph. This proportion will give me the clustering coefficient. Okay, now why 3 is being multiplied? Because a triangle can have a 3 different orientation: ABC, BCA, and CAB. If I can start from A, the triangle will be ABC. If I start from B, the triangle will be BCA. If I start from C, the triangle can be CAB. If my direction is fixed as clockwise or anti-clockwise. Okay. If I'm taking care of clockwise and anti-clockwise both, means ABC and ACB, then the multiplying factor will be 6. So ABC and ACB, then BCA and BAC, then CAB, BCA, CAB and CBA. Okay, so there will be there now. If direction also matters, then the multiplying factor will be 6. If only the orientation of those triangles ABC, BCA, and CAB in a positive in one direction only, then it will be 3. Okay, so that is a global. Local or individual vert. So this is related to entire graph, and clustering coefficient related to the individual vertices. The local clustering coefficient to a small world phenomena. How about the path length? Small world phenomena means the path length of that node to every other node of a graph. Eccentricity of that vertex will be its local clustering coefficient. Okay, so questions regarding this?
Sir, one question on the property. Just
This one?
no, on the clustering coefficient. Yeah, the second point.
Where it
Yeah,
is?
yeah. The clustering coefficient is a measure of degree to which. Next slide.
Next means previous.
Clustering coefficient. Yeah.
Acha, yeah.
Yeah, the second point, actually, I didn't quite get this one. The clustering coefficient is a measure of degree to which the nodes in a graph tend to cluster together. That means the overlapping nodes you mean by this or what?
No, not the overlapping nodes. Cluster together means in terms of connectivity, means in terms of reducing the path length, means tends to cluster together, means they needs to connect together with a lesser path length.
Okay.
So that means if my clustering coefficient is high, so that means there are more number of triangles. So that means this denominator is fixed. Now clustering coefficient will be more if there'll be more number of triangles.
Okay.
Now, if there is more number of triangles, what is the interpretation? A graph. Suppose, for example, initially the graph was this. It was having, suppose, 10 triangles. Suppose, for example, 10 triangles in terms of closed path. Okay. Now the triangles increases. So what does it means? Let me explain you in that way. Initially, my graph was something like this. There is no triangle.
Right.
If triangle increases, this will not increase. Okay, so in that case, now we have 1 triangle, 2 triangle, 3 triangle, 4 triangle. What had happened to the graph? The nodes of the graph are connecting
more
together.
nodes will be connected to each other. That means, right?
More nodes will be connected to each other and the graph will become dense.
Okay.
If I increase the the number of triangles more. Okay, in
Mhm.
this way. This is again a triangle now. 1, 2, 3. If I'm
Right.
increasing the number of triangles, what is happening?
It is moving towards the complete graph. So maybe
Moving
complete
towards the
graph.
complete graph. Now read this sentence. Clustering coefficient is a measure of degree to which the nodes in a graph tends to connect together in a dense form. Cluster together means connectivity, dense connectivity.
Okay.
Okay, so
Okay.
cluster means dense connectivity. So that means nodes are it is the we can say proportion, or we can say it is the value by which we can say, okay, so that means nodes are coming together densely, or they are connecting together in a dense way. So that clusters are being created.
Okay.
So
So
they
does that mean the complete graph would have a clustering coefficient, higher clustering coefficient?
highest,
Okay.
it will have the highest clustering graph, because all the three will be a triangle. So numerator and denominator will be same. So
Mm.
complete graph will have a clustering coefficient equals to 1.
Oh,
Clear?
okay.
Now is this clear? Clustering
Yes.
coefficient is a measure to a
One
degree
or
to which
three actually. Three or one.
matlab it should 3 multiplied by so that means the number of triangles and number of triples will be same. This value, this factor will be denominator and
That will be one.
numerator.
Okay. So
Uh,
okay.
this
Okay.
3
Thank you.
is just nothing. This is 3 is the orientation.
Orientation. Okay. Got it.
In how many ways, in a clockwise direction or on anti-clockwise direction, if in one direction, how many ways this triangle can be represented? 3. But this numerator and denominator will be same. Clear?
Yes, sir.
So the max value of C is 1, is it?
If I'm not bothered about the orientation and the connectivity, but if my main focus is number of triangles in a graph divided normalized by the connected triples in a graph. Usually, whenever we divide something, means we are normalizing those values. So number of triangles normalized by the number of connected triples. So this proportion will be equals to 1. 3 is just the 3 multiplication is just a taking care of orientation. Clear? So it will be 1. In this case, if 3 is the factor which is multiplied, then the max value will be 3. Is it resolved?
Uh, yes, and if we have C equal to 1 or 3, that means it is a complete graph. And in the data perspective, that means we have a diverse data, right? Well connected data. I mean,
Ha,
what does practically it means?
practically means totally connected database. But
Okay.
in a real time, complete graphs are very rare, because the graph itself is a size of 1 million node. Then in a 1 million node, it is impossible to have a complete graph. In that case, now the relaxed version of complete graph is the keyword which has been used as a relaxed version of complete graph is click. CLIQUE. Click is a near complete graph. Clear?
Yes.
Okay. Any more doubts? Now that line, the number of triangles delta I and node I is related to the clustering coefficient of the graph. How many? Okay. So there are some dynamics related to the dynamic graph, means the graph that changes with respect to time. They may grow, either shrink or split as the time passes. Clear cut? So densification means most real world, I can read those. So most real networks such as web and social network continues to become more denser over time. This law states that the number of nodes in the network increases. So this I have to explain. The number of nodes in a network increases superlinearly, means with a very high exponential power with the number of nodes over time, whereas the number of edges also increases superlinearly over time, and that too with a far more larger rate than the number of nodes. Reason: suppose this is my well connected graph, which is almost complete with a very high density. Okay, having suppose 10 to the power 7 node, and internal connectivity will be maximum connectivity will be 10 to the power n into n minus 1, means 10 the for the complete graph, the number of nodes will be, number of edges will be n into n minus 1. So that means every node is connected to every other node, means 10 to the power 14 minus 1 edges. Okay, so minus 10 to the power 7 nodes and 10 to the power 14 minus 1 edges. Ideally, it should be, if I say my graph is complete. Why? Just by using that n into n minus 1. If it is undirected, then 2. Okay, so by 2 means 5 into 10 to the power 13 minus 1, suppose somehow. So equivalent to 10 to the power 15 only. Okay, 10 to the power 14 somehow. But it is not 10 to the power 7 minus 1. So 10 to the power 14. चलो ठीक है, डायरेक्टली लिख देता हूँ यार, 10 to the power 14 minus 1 by 2. यार इरेजर लेना था. So 10 to the power 14 minus 1 by 2 will be the total number of edges in the graph. That is very huge. Okay. Now, if I add a new node in a graph, okay, fine. So how many number of nodes will be? 10 to the power 7 plus 1 node. Okay. And so if I want to make it complete, then how many edges this node should have? It should be connected to every other node by a direct edge. So this new node should have 10 to the power 7 new edges. Am I correct? How many? If I want this graph to be complete, then that means it should directly connect to every other node of a graph by a direct edge. So how many nodes are there? 10 to the power 7. Now how many new edges will be there? Again 10 to the power 7. 10 to the power 7. So in a new graph, so this is now G prime with the new, this is G and this is G prime. Okay, so G was having 10 to the power 7 nodes with certain edges, I assume to be complete. If I add a new edge, new node in a graph, and I want my graph to be complete, then I'll have to add 10 to the power 7 new edges. Okay, so I have added one node, but I'll have to add 7 to the power 7 new edges. So that means even in this number of nodes, it exhibits the triangle power law. So that we call it as densification power law. So where NT is the number of nodes to be added and ET is the number of edges to be added. So in that case, ET is proportional to N to the power NT to the power alpha. Okay, so that means number of newly number of new edges will be far more greater than the number of new nodes in a graph if I'm dealing with a dynamic graph. So this is G1, GT at time t, and this is G at time plus 1, t plus 1. Okay, so that means GT, previous graph, GT plus 1, the graph at a next instance of time. So what is the difference? One new node and 10 to the power 7 new edges. In an ideal situation, if I assume my graph to be complete, if click almost complete graph, then the value will be lesser, but still the number of edges will be far more as comparison to node. Node is just only one, but suppose for example 100 or 1000. So every new node adds 1000 new edges in a graph. That also super linear. So this law is also exhibits the power law. So I'm not implementing the power law, I'm just observing the power law. This power law will be there. So every activity in a graph exhibits the power law, real-time graph. The other dynamics is shrinking diameter. Shrinking diameters means as the connectivity will increase, the diameter of a graph will decrease, obviously. So average path length of an 2 MSN messenger comes out to be 6.6. So that's why a general term was coined in the year 2006, 2008, which they call it as 6 degree for separation. Okay, so diameter shrinks over time. Edges are added more rapidly to the network than nodes. So as more number of edges are added to the graph, it becomes possible to traverse from one node to another with a fewer number of edges. So that's why the diameter will be less. Clear? You can go through those papers which are mentioned at the end towards the bottom of those papers, and those papers are different everywhere. So whatever I'm claiming is being supported by the references. So you can go through those references if you want to read more, if you want to understand more about the content which I'm talking about.
Sir,
Okay, so
I
it's
have a
not the
question.
Ji, boliye.
So you have mentioned like 10 to the power 14 in beginning. So like how 14 has come? I missed that
Achha.
point.
No, no, no issue. 14 is just I'm assuming that it is a complete graph. So if the initial graphs contain 10 to the power 7 nodes,
Hmm.
so a graph to be complete, there has to be n into n minus 1. So total number of edges in a complete graph are n into n minus 1 by 2.
Okay.
So that's why so 10 to the power 7. So how many number of edges will be there in a complete graph of 10 to the power 7 nodes? So 10 to the power 7 into 10 to the power 7 minus 1 by 2. So
Okay.
this that's why it is 10 to the power 14 something. So 10 to the power.
Okay. Yeah, got it. Thank you.
It should be. Acha. Huh. So 7 minus 1. Suppose, for example, if it is confusing you, you can assume it to be 1000. So 1000 into 999 by 2. So
Okay. Yeah.
1000 into almost means almost double. Matlab the same value is multiplied together again. So
Yeah,
that's why
got
it was approximately 10 to the power 14 minus 1.
it.
Yeah.
Okay. Yeah. Thank you, sir.
Any more query? Okay. Okay. Last half an hour. I forgot to take a break. Can I have a break of a minute so that I can have some water?
Yes, sir.
Thanks for the permission, but I started the activity before your permission. Okay, fine. So there was one more researcher with the name McLuhan in the year 2010. He noticed that he was studying the effective diameter of a graph what he noticed was in that graph, so structural analysis of a network observation and application, it was his PhD thesis. So what he observed was that there are some point, so there is an often point in a time, we call it as gelling point, where the diameter spikes away. Okay, either go up or go down. So obviously the diameter will be going down. Now before that point, the graph typically consists a collection of small disconnected components. So the graph was having disconnected component, okay, with certain small diameters. The more and they have been coming close together means the graph is becoming dense, and so that is again related to dynamic graph. So with respect to time, the connectivity was increasing. Okay, and some new nodes were added into the graph. And suppose, for example, if a new node is added and that connects both the component that generate an edge between two different clusters. So what is the immediate outcome? Now these are not two disconnected component. Now they become a merged connected component now. Okay, with respect to time. And initially there was something like this. So there was some two not this way. There was some two connected two components connected together by a single edge. Okay, by a single edge. So this whole path, this whole bunch, and they connected together by a single edge. And then when the number of nodes increases and the connectivity increases, then it becomes again a oval shape. Now, the moment those two clusters merge together to form a bigger cluster, that point was called as a gelling point. And suddenly the diameters vary. So that's why at this point, when the component were merging together, they were giving rises to a spikes at that time. So before that point, the graph typically consists a collection of a small disconnected component. But at this moment, at this gelling point, this point he called it as gelling point. So this gelling point seems to be a time where a giant connected component is forms and takes off in the sense of vast majority of nodes belongs it. Means those small connected components was merged together to form a bigger component. So I've just taken an example of a single node. It may be 15 nodes that may have added together. 15 nodes and suppose 10,000 edges. The diameter suddenly have changed. Earlier it was because of those small components, so diameter might be smaller. Now it is a bigger component with a higher diameter, and then slowly that diameter is coming down. So that's why there was a spikes in a both at the top and at the beginning, at the bottom as well. Okay, making it so in that case, a new node appears that mainly tends to join that giant connected component, making it even larger. So he call it as a giant connected component in the gelling point. So that point of time where there was a spike found in the diameter of that graph, they call it as a gelling point. So giant connected component, and then other NLCC means the other non-largest connected component. There was multiple connected component. Some was giant, some was non-largest connected, some was non-giant, smaller one. So they call it as NLCC, non-largest connected component. So this was the observation that he made. Okay. He also noted in his PhD thesis about the power law in terms of weights. So he performed an experiment on a weighted connected graph. Okay. So he plotted the values between the number of edges and the weight of the graph. So ET and WT he plotted. So with the number of edges and the total weight of a graph at a particular time t, the dynamic graph, and he observed that the weight of the graph was also increasing in terms of power law. So they also follow the power law, and he called it as a weighted power law. Okay, so all these observations of the power law was not being included into the graph. They were observed in a graph. All the activities, whatever you do, either in terms of degree, in terms of connectivity, in terms of weights, in terms of number of nodes to be added, number of edges to be added, all the activities, they were obeying the power law. The count, the number was in accordance with the power law. Means with a small change, there was a huge increase or a decrease in certain parameters. Clear? Clear? Although I'm devoting much of the time in this power law, but power law is something which, if you can find out that it is there in the graph, then that means you can say that those graphs are realistic, because those activities are being observed everywhere. Okay, last two slides, and then I'll quickly finish this module. But before that, any query? And then I'll start a new module then. Okay, fine. So there was another researcher, Sudhir Tyro et al. Sudhir L. and Tyro et al. They also observed one small thing. They also performed. They didn't much. They didn't do much. In the year 2002, they just arrange the nodes of a graph of internet based on their degree. So in a simple conceptual model of an internet, what they did is they perform the web scraping on the internet. Okay, on those autonomous systems based on the intermediate connections, the switches, routers, and servers and all. Okay, so they arrange those degrees of those intermediate components in the internet, and they observe one thing. When they arrange it, what they observe, the observations was unique. They found a core in an internet. Internet means in terms of connectivity, network, switches and routers, and those PCs, okay, connected through those switches and hubs. So they observed that there's a core that consists the highest degree of the node and the click. I think I have already explained you the click. Click is almost complete graph. Not complete, almost complete, because complete graph is again a hypothetical term. In a smaller graph, it's easy. But for a real-time graph which is very huge, it is impossible that you will found a complete graph. Then you'll have to have a relaxed version of a complete graph, which is click. So that was almost a click, means complete graph, and those number of nodes were 8 to 13 only. Okay, so that means there were a smaller number of nodes having the highest degree. Okay, suppose for example, the graph was of 1 lakh nodes, then there were 8 to 13 nodes having degree 99,000, or we can say 90,000. 10, 9, 1, 2, 3, 4. Unit, tens, 100, 1,000, 10,000. So 90,000 degree. There was only 10 to 15 nodes having degree of 90,000. So it doesn't mean that, okay, so there were few nodes having 8 to 13 means the highest degree was 12. No, the graph was of 1 lakh nodes. So there were only few nodes having 90,000 degree or something, 80,000 or whatever it be, wherein the highest one. Okay, whoever has the highest was, or we can say in the higher range was very few. Apart from this, so that means again a power law. Very few nodes having highest degree or a higher degree. Then so they they call it as a core. Then they found layers around the core in terms of degree, in terms of connectivity, arranged based on the connectivity. Okay, so they found layers around the core in the form of concentric circles. Layer further from the core have a lower importance in terms of connectivity. Okay, or in terms of importance also, but when the moment I say importance, I'll have to come up with the criteria how I should measure the importance. As of now, this importance is terms of connectivity. Okay, so there later around the core, we were having different nodes having lesser connectivity than the click, than the core. So suppose 50,000, then 10, then 30,000, then 10,000, and so on. So there were concentric circles with a different or lesser connectivity. Okay, and then there were large number of nodes, around 40 to 50% of the nodes, who were hanging. Hanging nodes means nodes with degree 1. So again, there are large number of nodes having smallest degree. What is the smallest degree? 1 in that case. It can be 0. 0 means isolated. But if that would have been isolated, it should not be a part of internet then. So that's why the degree 0 cannot be included. If I'm talking about internet, means international network, means if I have a simple PC without a Wi-Fi, without a LAN, without internet, it will not be counted in an internet now. This is a standalone PC. So that's why 1 degree is the minimum. Why not 0? Somebody should come up. Okay, why should not be 0? Means a node with degree 0 is isolated node. Then if it is isolated, it will not be a part of network now. Okay, fine. So in that case, there were 40 to 50% having a 1 degree node. Person like me who are not participating in anything, were just connected to internet. Okay, so this was the structure that they identified for the internet, and they call it as jellyfish structure. So this is the structure that they propose about the internet. Questions? Fine.
Sir,
Ji.
like previously you were discussing about this power law. So we were having this triangles in a graph. Now here we came to know circles. So is it like we are studying about the different kind of graphs through research paper?
No, these circles are the number of nodes with certain degree. So suppose, for example, if my 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so this core contains 10 to the power 5 degree. This circle contains all the nodes. So that means 10 to the power 5 degree means 8 nodes having, suppose for example, 15 node. There are only 15 nodes having degree of 90,000.
Okay.
That means you can count. Triangles are something different. Now, high connectivity means this is only because of triangle.
Okay, so power law exists here also. Okay.
Power law is everywhere. It's like gravity, it's like air.
Okay.
Okay. So high connectivity because of the power law only, because of the higher number of triangles only. Even in this, so there were there were suppose around suppose 1,000 number of nodes having degree 90,000. Okay, if it is 90,000, then 80,000. Okay, so there were all the nodes having degree 80,000 were put in one set.
Okay.
Then there were few who were having all the nodes having degree, suppose 75,000. So suppose there were 1,000 node having degree 70,000. So 1,000 node having degree 70,000 means every node has at least on an average have a degree of 70.
Okay.
Okay. Degree 70. There will be triangles, but not to the maximum. There will definitely there will be triangles, but smaller number.
Okay. Yeah, got it.
Okay.
Thank you.
So please do not be confused with those circles and triangles. Triangles is in terms of connectivity. This circle is the number of nodes belonging to the same category in terms of connectivity.
Okay, got it.
The internet switches or we can say routers having this degree.
Okay.
So those circles are the, we can say, um, uh, in geography, uh, all those lines having the same temperature, what we call it as
I
ISO.
don't remember.
Is there any this
Isothermal.
isothermal or something? So all those nodes having the same degree, they are connected together. So they are not the circle, matlab all the places having the same temperature, they are connected together.
Okay.
I think something related to isomer and isotopes are related to chemistry. Something iso related to geography. When there's a lines, isotopes, something whatever it be, but connecting all those points having the same property. So those are the circles.
Yeah,
So
got it.
connecting all those components having the same or similar degree. So that's why they were called as circles, because they'll have to just not necessarily they come up with a circle because they coined the word jellyfish. It should be the case that they should have come up with the squares as well in that way.
Yeah.
It can be in that way also. They can represent that in that way, like a pyramidal shapes. Something they should have come up, but they come up with a triangle because they just try to justify the structure in terms of some relevant thing. So they called it as jellyfish. If someone would have opposed and they might have come up with this structure like a pyramid form top.
Okay.
Maybe just a name coined by them. And so these are not the circle. This circle are in with respect different perspective, and triangles are different. Triangles are something different. Triangles in terms of connectivity, internal structural connectivity from the neighborhood.
Okay.
With respect to each graph. So please do not be confused with triangles and those circles. Geometric shapes. Fine.
Thank you, sir.
Any more queries? Okay, fine. The last thing is, there was one more mathematician, there was one more researcher who performed the web scraping on www, and then he come up with how does www look like. Almost similar, but in that way. So he performed a web scraping on World Wide Web, all those web pages and their links, and that will be a directed graph. Okay, border at all, the same which had come up with the degree power law, in degree and out degree power law. Okay, and this is the paper. So he performed the web scraping on www, and then he come up with a structure of internet. What does he call? What does he state? He state that the core is a very strongly connected component. So strongly connected component in terms of triangle, in terms of internal connectivity, structural connectivity. So that SCC he put it in between. Then the another component he call it as in component. Okay, so in component have all the directed path, means in component have all those web pages who are directly connected to the web pages that belongs to SCC. So he call it as in. So in component, each node in component has a directed path, sorry, not direct edge, a directed path to all the nodes in the strongly connected component. They are pointing towards Google or Yahoo search pages, something which belongs to the densely connected part, strongly connected component. Then the another structure, another part of that structure, he call it as out component. So out component were all those web pages who were directly reached by the node of strongly connected component. Means the strongly connected component have an outgoing edges to those set of web pages. So each node can be reached by direct path from the strongly connected component. Okay. So he call it as that bunch of web pages as an out component. Then there were few tendrils. So tendrils means hanging around. So some nodes. So these are the web pages which can reach some web pages in out, and that can be reached from the web pages in an in without going through SCC. So they have nothing to do with the SCC. They are not connected to SCC. They're just roaming around. They're just hanging around. Okay. Sometimes it was connected from in to out. Those were called as tubes. So there were few web pages. They were directing from the in component to the out component. So they all put into the different category of connectivity. We call it as tubes. Sorry, he called it as tubes. Okay. And then the remainder of those web pages falls in the disconnected components. So all those web pages who are neither pointing out to SCC nor being pointed out by in component or nor pointing out to out component. So they're not part of it, but somehow they are connected together. So suppose, for example, the search engine of China. Okay, so whatever search engine of China is, all the other web pages are not being accessible. Neither they are connected to all the web pages of the internet or something, or this may be the disconnected component. This may be the search engine of North Korea. So they may be disconnected component. It's not the case that disconnected component are the web pages which are not pointing out to anyone. Okay, again, degree 0 is not possible if I'm talking about connectivity. Degree at least 1 in this way, or a club of something else. So the remainder of web pages falls into the disconnected component. Okay, and he club all together and name it as a bounty structure. So the structure of www was going to be a bounty structure by him. They all did nothing. They all just perform the web scraping and somehow play with those numbers and then draw a graph and come up with a conclusion and get their paper published. Because at that time we were not knowing how does the structure look like, what is the structure of www, what is the structure of internet. No one was having any idea. So they come up with that idea and then get their paper published. Unfortunately, I won't be able to start it, but okay, let me beat around. Let me give you a brief introduction about what we are going to cover in the next session. So next session, we are going to start away with the next module. Again, we will be keeping in this, we are moving in the same direction of structural information. Okay. So about the other network measures, we will try to find out the other values which can be used to infer something about the graph, or we can say the numbers which can be extracted out from the graph based on their connectivity. Okay, so that we call it as network measures. I should not start it. Should I?
Sir,
Okay.
maybe I have a question on the previous slide. The last slide we were discussing, the
Should I
SCC.
open it?
Yeah, means
Is it visible, or should I make it as a presentation mode?
yeah, this SCC component. Actually, I didn't quite get this sentence. Each node in SCC has a directed path to any other node in SCC. What does that mean actually?
Means the web pages, matlab is strongly connected component. Okay, so that means all those web pages whose in degree or out degree is very high. So these are the web pages. Okay,
Right.
web
But
pages.
does it mean like means in terms of graph, if we keep away the web pages, in terms of graph, is it like each node is connected to each node, kind of
Ah, in terms of degree,
degree?
in terms of connectivity, direct edge, or we can say not direct edge, sorry, direct path. Sorry, wherever I'm using a direct edge, it means a direct path. Means in terms of connectivity.
Each node in SSC has a directed path to any node. Y-
Web link means it's not
You mean
means
does
web,
that mean that each node can reach to any of the other node either directly or by or via some other node? Is
ha, through some other node using those hyperlinks.
okay, got it.
Now, in a hyperlink, suppose for example, in a Google, you doesn't have this back and forth button. Suppose for example, you didn't have this back and undo button. Now,
Hmm.
if I start with something by google.ai, okay, suppose I didn't have I start with something, okay, it takes me to something else, okay, I do not have any back button. Then from there, I'm moving to other quick links or somewhere I'm moving around.
Mhm.
So in this way, I'm converting this navigation in the form of a graph.
Okay.
Sir, last time we have a I mean information retrieval subject, and there we studied web crawling. So there also we have the similar concept, like strongly connected components. So that for web crawling, that when we retrieve the information from different going from different pages to different pages. So is it the graph is what we need to understand, that how these are related?
So ultimately, web crawling in a the crawling that you have performed on the www is what nothing. It is just a node. You visited a node,
Right,
then execute, then click on any of the hyperlink. So that web page may contains multiple hyperlinks. So
exactly.
first hyperlink, you move to the next page. It
Correct.
may contains multiple hyperlinks. So using the second hyperlink, suppose for example, you move to the other page, and this is how you are converting. You are performing the performing a scraping on a www.
Right.
So either in a DFS manner or in a BFS, most probably in a BFS manner.
Mm-hmm. Right, sir. Thank you.
And this is what they were talking about. So if you have performed, this is again the web crawling is the basis.
Okay.
So web crawling is the underlying activity that you will have to follow.
Understood, sir.
Web crawling is the underlying activity for coming up for with even for the trying for the structure of internet, even for the structure for internet also. In that case, web crawling will be in a different way, finding out the internet in terms of message passing. This can be done through the message passing, just by observing the intermediate, we can say, um, intermediate components in between.
Okay,
Okay.
sir.
So
Thank you,
now,
sir.
thank you. So in that case, by mistake, few times I have directly said direct edge, but It's not direct edge, it is a path from one node to another node. Okay, directed path. Clear?
Yes.
Okay, I think it's already over past the overshooted the time, so I think I'll have to stop. I'm stopping over here. Unfortunately, I was intending to cover the start the network measures, but no issue. The pace will not be on the cost